The machines are powered down. The assembly line is completely still. Our output today is exactly 0. But as soon as the garage door opens, a bill is waiting. This is the reality of fixed costs. These are business expenses that stay exactly the same, whether you are churning out 1,000 hyperdrives a day or sitting in the dark doing nothing. Rent, loan interest, insurance, the meter is always running. If we map this out, we put our output quantity on the bottom axis and our total expenses on the side. To represent fixed costs, we draw a perfectly flat horizontal line. It doesn't matter how far right we move along the quantity axis, that expense never bends. Then we have variable costs. These are the expenses tied directly to the volume of things we actually make, like raw metal or energy. When our output is 0, our variable costs are also exactly 0. To calculate our actual financial burden, we combine the two. Total cost is simply the sum of our fixed costs and our variable costs. Look at what happens to the total cost curve when output is 0. It starts right here, at the exact same point as our fixed costs. Because those baseline expenses exist regardless of volume, simply existing is an active financial drain. To survive, a business has to start the machines. As the power grid hums to life and we push production from 1 unit up to 10, materials start flowing in. We buy steel, pay for electricity, and deal with supplier prices that shift by the hour. As the volume scales up, looking at the total expenses isn't enough to tell us if we are actually running efficiently. To figure out the true financial weight of what we're building, we have to calculate the average costs per single unit. We start by isolating that baseline rent. We take our total fixed cost and divide it by the quantity of output. This gives us our average fixed cost. This graph plots average fixed cost. It starts incredibly high on the left. Watch what happens as output increases. The curve slopes downward. This is spreading the overhead. That rent is diluted across hundreds of items instead of one. The math heavily incentivizes volume. The more units you push out the door, the cheaper your baseline infrastructure becomes for every single product. But rent isn't our only expense. We calculate average variable cost, variable expenses divided by quantity, and finally, the ultimate metric, average total cost divided by quantity. Average variable cost dips initially from discounts, but climbs back up as the workshop crowds. Layering average total cost creates a mirroring U-shape. The vertical gap between them equals average fixed cost. As volume increases, curves converge but never touch. While increasing your volume helps absorb the fixed costs, the eventual spike in variable costs creates an efficiency trap. Every producer has to navigate this balance. Intrigued, focused. Avoiding that trap means finding the absolute lowest point of the U-shaped average total cost curve. This specific dip marks the point of maximum per unit efficiency. It applies to our small garage operation, and it applies to a galaxy-spanning monopoly running planet-sized factories. This textbook chart shows exactly why. Even with billions of credits in total expenses, those massive factories are bound by the exact same U-shaped laws of average variable costs and marginal efficiency. By tracking this specific curve, a producer can pinpoint the exact number of units to build each day. They stop pushing the assembly line right before the costs start curving back up. Let's review the anatomy. Fixed costs stay flat. Variable costs shift with volume. Total cost combines them. Average fixed cost slopes down forever, and average variable and average total costs form the U-shape. Understanding exactly how these mathematical lines interact is the only way to keep the machines running. It is the dividing line between running out of credits and building a profitable empire.